My name is Pavel Paták, and today I will tell you a few words about our construction, which shows that shellability of balls is an NP-complete problem. This is a joint work with Martin Tancer. The construction also shows that deciding whether a simplification complex embedded into 3 space is shellable is NP-complete as well. And it also proves NP-completeness of collapsibility for simplification complexes embedded in the 3-dimensional space. So let us start with the definitions. A simplification complex is a collection of simplices that intersect in a nice way. I recall that a simplex in dimension 0 is a point, in dimension 1 it's an edge, in dimension 2 it's a triangle, in dimension 3 it's a tetrahedra, and so on, even in higher dimensions. And if I say that these simplices have to intersect nicely, I mean that if I take 2 simplices of my simplification complex and intersect them, I again obtain a simplex which is contained in that simplification complex. And the simplices of the simplification complex K are called its faces. So you may ask, why do we care about simplification complexes? Well, simplification complexes can be used to model more complicated geometrical shapes, and they can also be used to model topological properties. And because of that, simplification complexes have found applications throughout mathematics and engineering. A facet of a simplification complex is a face that is not contained in any larger face. And a simplification complex is called pure if all its facets have the same dimension. Yeah? So, for example, if I have a pure 3-dimensional simplification complex, that means that I have a collection of tetrahedra that are glued together along faces, along triangles, edges, points. Since a simplification complex is just a bunch of simplices that are glued together, I may ask for a pure simplification complex whether this gluing can be done in some nice order, whether I can order the facets in such a way that each facet is glued to the previous one only along its d-1 dimensional faces. So, for example, I may glue triangles only along edges, not along points. And similarly, I can glue tetrahedra along triangles, but not along edges or vertices. Here we have an example of a shellable simplification complex. And the complex is called shellable if this nice ordering of facets is possible. But if we want to glue this next red triangle to the green ones, we cannot, because it intersects the previous one only in those 2 points, and that's not allowed. And similarly, we cannot glue this red triangle to the previous ones, well, because it intersects them in an edge, which would be okay, but also in a vertex on top, and that's forbidden. If we have a shellable complex, we may count the number of facets that were glued along I d-1 dimensional faces. This number is called hi. So, for example, in this picture, h2 would be the number of triangles that are glued along 2 edges. Why do we care about shellability? Well, shellability is an inductive procedure how to add facets while keeping nice properties throughout the construction. So, as such, shellability has found application throughout mathematics. And let me just mention some of the applications. In polytope theory, shellability is used in the proof of Dan-Somerville relations for simple shell polytopes, where it states that the number hi equals hd minus I, where d is the dimension of the polytope. It also provides the upper bound theorem, which basically boils down to the fact that the number hi is upper bounded by the hi of the cyclic polytope. It is related to lower bound theorem, which basically boils down to the fact that hi is larger or equal to 0 for shellable complexes. But shellability has also found application outside polytope theory. Let me just mention PL topology, the shellability of partially ordered sets, or even some applications in algebra where it was used for proving some properties of shellings of monoids. As you may have guessed, not every simple complex is shellable. Even not every pure simple complex is shellable. Here we see an example. We cannot glue these two triangles along an edge, right, if they share only a single vertex. However, there are also examples of simple complexes that are homeomorphic to balls and that are non-shellable. Yeah. And the same also holds for spheres. This indicates that deciding shellability may not be an easy problem. So let us study the complexity of shellability. First of all, shellability is obviously in NP because we just need to find one single ordering of facets, which is a shelling, and testing whether a given ordering is a shelling is easy. So in 70s, Danarash and Klee asked whether shellability is efficiently decidable. They were mostly interested in shellability of balls and spheres because they related this question to the balls and sphere recognition problem. Okay. They also showed that shellability of two-dimensional pseudomanifolds can be tested in linear time, basically by greedy algorithm. And here by a pseudomanifold, we mean a collection of triangles where every edge is in exactly two triangles. For a long time, the complexity question even for general complexes remained open until recently, where we, together with Xavier Goaok, Zuzana Patáková, and Uli Wagner, showed that this problem is NP-complete starting from dimension 2. Our construction was then slightly simplified and said in slightly different language by Andrés Santamaria Galvis and Raz Woodruff. However, there remained several open questions, right? The original question for balls was not answered, and the constructions were also not embeddable into the three-dimensional space. So it was not clear whether shellability remains NP-complete even for complexes that can be represented in the tree space. In our work, we have provided answer to some of these questions. For example, we have shown that it is NP-complete to decide whether a given triangulation of a d-dimensional ball is shellable, and that's NP-complete for all dimensions d which are at least 3. We have also shown that deciding whether a two-dimensional complex is shellable is NP-complete, and that even if this two-dimensional simplicial complex is embedded in the tree space. And moreover, our last result also tells that it is NP-complete whether a given three-dimensional simplicial complex which is embedded in R3 is collapsible. Since we haven't defined collapsibility yet, let me now tell what this collapsibility is about. A phase tau of a simplicial complex is free for collapse if it is contained in a unique facet, sigma, different from tau. And if this is the case, we may push this tau inside of sigma without changing the homotopy type of the complex, thus maintaining most of its topological properties. A simplicial complex is then called collapsible if it can be reduced to a single point by a sequence of collapses. For example, here we have an example of a complex consisting of 4 triangles, which is collapsible. For example, this red edge is free for collapse, and if I collapse it, I remove this face and everything which is above it. That means the triangle. Then I have next free edge, another free edge. Then, for example, this vertex is also free because it's contained in a unique triangle. I may remove it, and so forth. In the end, I obtain a single point. Hence, the original complex was collapsible. We note that collapsibility is a combinatorial equivalent of contractibility. Yeah, a topological space is contractible if it can be continuously shrink into a point. And unfortunately, deciding whether a given simplicial complex is contractible is an undecidable question. On the other hand, collapsibility is obviously in NP, hence decidable. And our result, nevertheless, tells that it's not an easy task because deciding whether a three-dimensional simplicial complex is collapsible is NP complete. And that even if that complex is contained in the tree space. Let me tell you a few words about our proof strategy. And since the proof for collapsibility is the easiest one, we shall focus on it. Our aim is to build for each instant of so-called planar rectilinear monotone 3-SAT a simplicial complex which is embedded in R3 such that this complex is collapsible if and only if the original instance of the planar rectilinear monotone 3-SAT was satisfiable. And since the planar rectilinear monotone 3-SAT was shown to be NP complete in 2010, this will prove that collapsibility for three-dimensional simplicial complexes embedded in the tree space is also NP complete. So, what is the planar rectilinear monotone 3-SAT? So, what is planar rectilinear monotone 3-SAT? In planar rectilinear monotone 3-SAT, the variables are drawn along the x-axis of some plane, and the clauses are also drawn as rectangles, which are either above or below the x-axis. And moreover, we require that if the clause is above the x-axis, all literals in it are positive, meaning there is no negation, and conversely, all the clauses below the axis are negative, meaning that all variables in them are negated. And each of the clauses is connected via a straight vertical line to the corresponding variables. And so let me say a few words about how do we represent variables in our construction. And a variable gadget in our construction is simply the join of a boundary of a triangle with an edge. Or in other words, they are three tetrahedra which are glued together as follows. So let us also specify how our variable gadgets interact with the other gadgets. For that, we glue some other gadgets, which we shall specify later, along these black edges. And we also glue some other gadgets to this blue edge, and symmetrically there is another blue edge going to the back. Yeah? And now, because there is something glued along these black edges, if we start collapsing, we may collapse only from some of the triangles which are here. For example, we may start with the front gray triangle. Then we may collapse the complex in the following way. And this makes this blue edge free. Meaning that if in these other gadgets that are glued to this blue edge, this edge is only contained in a single triangle, we may start collapsing these gadgets from this edge. However, because of these black edges, we can only make one of the blue edges in our variable gadgets free. Another gadget that we used is so-called one house, which was introduced already in the earlier works. And how is this gadget connected to the other ones? Well, we have this pink edge, which is connected, for example, to the blue edge of a variable gadget, and as soon as this edge becomes free, we may start collapsing this thing, and if there is nothing glued along this green circle, we may collapse this gadget so that we are only left with the black edge and the red edges. And these black edges are glued to other gadgets, and the red edges are also glued to other edges, but they are made free after the collapse of. The next gadget that we use is so-called turbine. It consists of a plate, which is a complex that looks as follows. And we glue simply 3 plates together. And how do these turbines interact with other gadgets? Well, they have 3 pink edges, and as soon as one of the pink edges is made free, then we may collapse the whole part of this simplest complex, the whole turbine, to the black thing, yeah, which is glued again to some other gadgets, and make the red edge free, and hence propagate the fact that we made this edge free to make this red edge free. And here the important part is that it suffices to if one of the pink edges is free. So we are now ready to describe the proof for collapsibility. Recall that we are given an instance of a planar rectilinear monotone 3-SAT, and we want to build a simplicial complex that is collapsible if and only if the original instance of the problem was satisfiable. For that, we take our gadgets. On top we see our variable gadgets. In the middle we see the one house. Here we slightly changed its shape, but since we work with topological simplicial complexes, we may deform them, right? And similarly, on the bottom we have the closed gadget with a slightly changed shape, but while preserving all the important properties, like these violet edges are on the boundary, and so is the black edge, and so is the red edge, and they are connected and make a tree. So, with that in mind, we may glue these gadgets to the plane that represents the instance of the planar rectilinear monotone 3-SAT in the following way. Note that these walls which appear, these are the Bing houses, and if one of these walls crosses one of the blue Bing house, we glue this Bing house along the green edges of it. finally, let us look how we can collapse the simplicial complex if the formula is satisfiable. Yeah, for that, we pick a satisfying assignment, for example, true, 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 false, true. And then we collapse the variable gadgets by choosing the side, by choosing the gray triangle on the appropriate side, which makes the corresponding blue edge free, allows us to collapse the neighboring Bing house, which allows us to collapse the outgoing Bing houses, hence making some of the clauses free. Note that we could only collapse the Bing houses that were not crossed. Yeah? But then, by removing the walls which outgo from the innermost clauses, yeah, we may remove them, making further outgoing Bing houses free, collapsing more clauses that were farther away from the variables, and so on, until we are able to collapse all of these walls, and hence making this strip of Bing houses, or this strip of one houses that glued the variables together. Yeah, so we have this strip of one houses that holds the variable together. We may collapse it, hence the variable can be collapsed then, and we finally may collapse the Bing houses which were glued to the variable side which was not chosen at first. And hence we collapse everything down to the plane, and we are left with a single plane which is obviously collapsible and can be collapsed to a single point. And that is one part of the proof. Now we need to argue that if the original instance was not satisfiable, then we are not able to collapse our simplicial complex, but that follows from the properties of the variable of the gadgets. Let me say a few words about the constructions for two-dimensional simplicial complexes in R3. And here we use a result of Hachimori, which states that the second barycentric subdivision of a simplicial complex is shellable if and only if all links of the simplicial complex are connected and the complex itself is collapsible. With that in mind, it now suffices to replace the variable gadget with a hollow sphere. That means with the boundary of the original variable gadget. The proof of NP-hardness of shellability of balls follows the same idea. However, the concept of a free edge is replaced via so-called free tetrahedron. That is a tetrahedron whose intersection with the boundary of the simplicial complex built so far is a union of triangles. And our gadgets now are obtained by a suitable thickening of the previous gadgets. However, in this thickening, we really need to pay attention that we do not introduce new free tetrahedra, and we also need to make sure that if we glue these things together, we obtain a ball, which makes this part of the proof somewhat technical. As an illustration, see the triangulation of the variable gadget.